Good afternoon, Tech Nation. Welcome to Webinar Wednesday. We are excited to have over 300 registered attendees for today's webinar, which is eligible for 0.1 CE credits from the ACI. Let's get started by giving one lucky attendee a Tech Nation Tour t-shirt. Where is the highest place in Washington State? Answer now using the questions feature on your dashboard. While you are answering, I want to invite everyone to join us for the MD Expo conference, which will bring CE professionals from across the nation to New England for 3 days of learning, networking, and the latest advances in technology, products, and services. Registration is now open. Receive complimentary admission by using the VIP Pass compliments of Summit Imaging found in your Webinar Wednesday workbook. All right, and the winner of our Tech Nation Tour t-shirt is Dennis Austin. Well done. The correct answer is Mount Rainier. Tech Nation would like to thank our sponsor, Summit Imaging. Summit Imaging is an ultrasound parts and transducer repair company that can quickly address specific technical needs based on a foundation of outstanding rapid customer service. Our philosophy is simple. Make our customers heroes. Visit www.mysummitimaging.com for more information. Our presenter today is Kyle Grozelle, Manager of Global Education and Training at Summit Imaging. Kyle, you may begin whenever you are ready.
Thank you very much for the introduction, and thank you for tuning in, guys. It's quite funny. I was actually just on Mount Rainier last weekend. Beautiful place. So today we're going to talk about minimizing transducer failure through proper care and early detection. What we're going to learn today is ensuring safe and reliable transducers by promoting that early detection of common issues via regular maintenance. This is going to help lower the total cost of ownership for your facility. Basically, the premise is you may be repairing your probes more, but you're going to be doing it on a less impactful way, less damage, more of just regular maintenance. Hopefully you leave this webinar armed with knowledge as well as some information to take back to your teams, as well as infection control, imaging, and OR. But first, let's start with some basics. What is ultrasound? It's a medical imaging system that uses high-frequency sound waves to create an image in areas of the body, very similar to sonar. What is the benefits? Well, it's non-invasive, it's immediate, has many applications outside of the medical industry, as well as it can be turned very portable. How does this system work? Well, the system will send power to a transducer. The transducer crystals vibrate, emitting wave signals. It's called the piezoelectric effect. These wave signals travel into the body, hit a boundary between signals. Some get reflected back, and some will travel further. Reflected waves are received by the probe, relayed to the machine, and translated to an image. This basics is very important to understand because we're talking about sound and the Doppler effect. If anyone's ever watched the news, I'm sure your local news station probably touts the fact that they're double Doppler approved. It really comes down to image quality, the acoustics of how the probe works. So let's talk about different transducer types quickly. We have many different probes based on the applications they're used for. We have Doppler, which is actually just used for CW. These Doppler probes actually show the flow in front of the transducer face, so they will be used for something like an arterial study or cardiac, something where they're just trying to see the actual flow of blood across the face of the transducer. Then you have linear. If you look at the photo in the image on the slide here, we kind of have some flat-faced probes. Those are your linear transducers. These are used for low depth but high quality imaging, usually on veins, legs, things that are actually close to the surface of the skin, or cosmetics, as well as some mammo applications. Then you moved into curved arrays. Well, do the math, it's actually a curved array. The curved arrays are used a lot more for depth-based studies, things like OB, stomach searches, as well as things like difficult to image patients with livers, kidneys. Then you have endocavity, which is taking these curved or linear arrays and turning them into an endoscope. So you have vaginal probes, prostate, that are used to do internal studies. Volumetric is where things start to get complicated. Take something like a curved array, mount it to a moving head, and put it inside a oil-filled ball. This is used to actually create 3D passes without having to move the transducer. The transducer actually does the work for you. The downside is now we're talking about complicated mechanics along with the electronics inside the transducer. You have sector and phased array, which are our new modern transducers that are very similar to matrix, that use more crystals, more cross-hatching, as well as are able to image further into a patient with the same amount of power. These are digital, very intricate, and require a lot more maintenance and care. Then you have the bread and butter of most ORs, the TE probe. This is transesophageal. It is that back long distal tube that you see at the left side of the picture. Those are used to observe the heart during the study. They go down the esophagus and look at the heart from below the rib cage. These T probes can be exposed to a lot of chemicals during cleaning and disinfection. They can be damaged with instruments or even bitten by the patient. But they house the same amount of electronics as one of those large linear curved or matrix probes in a very small 1/4 inch tube. So you can have a lot of damage occur on these T probes very quickly. So let's talk about the construction of a transducer. This is a standard probe. We're going to go through and break down the standard probe and just talk about some of the areas that you want to look after. The goal here is to identify places that you can inspect visually, and when you have a visual cue of damage or perhaps just wear, when to send the transducer into your transducer care team so that they can actually repair the probe quickly and easily instead of having it become a costly electronics failure. So let's talk about the lens. This is a layer of material, often a rubber compound, that protects and houses the array, but also facilitates the transmission of the ultrasound waves. This is very important to remember that the makeup of that rubber compound affects how the waves travel from the crystals into the body. Everyone knows that you need gel or a solid contact in order for an ultrasound to work. So if there is a bubble in the material or even a gap, that ultrasound wave is going to accelerate to the point where it won't return back to the crystal and you'll have what's called a dropout. Or you may have something like distortion or a misrepresentation of image that can cause some misdiagnosis. The housing. This seems very simple. It is just a plastic housing that protects the electronics from outside. But one of the things that you need to visually inspect for is cracking or separation of the housing, because gel could be getting into the transducer and affecting it, or even damaging electronics. Secondly, the housing itself is often an attachment point for a biopsy guide or needle guide. And if the housing is compromised, that needle guide will no longer sit securely on the probe. Or even worse, the housing that was used to repair the probe last is not OEM standard, and the guide doesn't even fit. You have your strain relief coming from the housing. This is a thick coating that attempts to protect the cable from overflexing and damage. The important thing to note, though, is that thick section of cable is still flexible in itself. It is a strain relief. It's not a strain stopper. A lot of strain reliefs out there will harden over time and cause the cable to start breaking off. Strain reliefs are also the best place to inspect for image quality problems when you're talking about constant wave, because if you flex on the strain relief, it's stressing the cables inside, and you might actually have dropouts occur on your transducer. Cable. Well, it's pretty simple. It's a long harness of wiring coming from the connector to the probe handle. The most common problem we have with cables is being run over by cartwheels. These are very easy to identify, as you're going to have a nice big divot in your cable, but it might have actually cracked the coaxial lines inside the transducer cable. That you may have to have that replaced. Also, we have seen many transducers out there in the market that have aftermarket cables that are made up of weaker coax lines that will not transmit as good of signal to the transducer or break down more over time and cause noise in the image. You then have a connector strain relief. Well, this is just the opposite end of the housing strain relief and operates the same way. It may be hardened over time. You want to flex it and make sure that it's actually doing its job and not allowing the cable to have cracks or separation from the housing. Then you have your connector housing. This connects the transducer to the machine and houses circuitry boards and locking mechanisms that secure the transducer to the machine. The main problem I usually see with connecting housings is being dropped and damaged by being perhaps hitting the floor, or even worse, ending up in the liquid that the transducer is being disinfected with, or say a sink. There is no waterproofing to this part of the transducer, and when you do have any sort of contamination on it, you should try to clean it as much as possible or send it in for dehydration. On top of that, these are part of the grounding of the transducer to the machine. If they are not properly connecting to the machine, they will not establish a true ground and could put the patient at risk due to exposure. Inside that housing, there's connector pins and contacts. These are what engage into the scan head on your system. These are brass pins or copper pins, and often you can see discoloration or wear on them like any other cable or connector, and you want to make sure that they're cleaned and not exposed to any sort of liquid as much as possible. After that, you have a connector cover. Most of these are missing by the time you guys see the transducers, but if you do have them, use them as much as possible. It's just a rubber seal that goes over the end. Are there any questions, comments, concerns as we're going through this at this point? Well, we'll leave them for the end of this. Now let's talk about a TE probe. They are very similar, but we're going to talk about the distal tube and the handle. After that, everything's very close to an original probe. Now TEs have a head and distal tip that encloses an array, typically about the size of a postage stamp, even smaller. Now that distal tip needs to be smooth, constructed of solid plastic, and sealed entirely so the patient isn't exposed to any sort of electronics or even previous patient risk. The lens is often made again of a rubber compound that protects the array and facilitates transmission of ultrasound waves. But going back into older transducers, they can also be filled with oil as well as a steering mechanism to rotate the lens inside that oil. Then you have a bending section. This is composed of 2 distal beads and then a rubber. The flexible rubber tube that bends when manipulated is used to steer the distal tip when you're viewing different areas or trying to hook to see up to the heart. This is the weakest part of the transducer and is most often damaged, but also the easiest to repair. The bending rubber is meant to take the bites, the scrapes, the scratches, and if you're doing leakage tests in your hospital, you'll be able to identify failing bending rubbers and have the transducer repaired before you expose it to Sidex, OBA, or even stomach acid. Because once the rubber is compromised and the Sidex, OPA, stomach acid can get inside, that's when you're going to start doing real damage to the electronics, as well as exposing the patient to chemical risk. At the end of the bending rubber on either side are epoxy rings designed to make a snag-free transition, as well as a smooth and comfortable transition into the body, but also seal that rubber to the hard distal head and the tube of the transducer. These should be a nice, clean, solid plastic with no chips or snags in them, otherwise you're going to cause patient discomfort. And as they start to age, they'll turn gray, and you want to have them replaced as soon as possible before they fail and let the rubber come off of the transducer. Then you have your insertion tube. This is a 1-meter tube that goes between the handle and the head of the T-probe. This is also the last section of the T-probe that is actually waterproofed or liquid-proofed. It has depth markers every 10 centimeters that should be clearly identifiable. It's white paint on a black tube. This houses articulation lines, a drive line, electronic lines, and everything that manages the head of the transducer. Most often, these distal tubes or insertion tubes can handle patient bites, damage from, say, other medical equipment that might be stored around it, but they are often also run over or squished, compromised. They're crimped by, say, a machine or a table rolling over them, just because of lack of care in the OR, perhaps. You do want to be able to see the death marks clearly. If you can't see the death marks clearly, that means the tube could be losing its coating and needs to be recoated. Otherwise, you may be actually causing further damage to the tube because it no longer has its protective layer. After that, we have our transducer controls. And this is one of the most exposed points where infection control often gets liquid on the transducer, or even dunks it into the sink with the transducer while cleaning it. And then that liquid is able to travel down the tube and damage the head of the transducer from the inside. On there's knobs that can be turned to facilitate the articulation inside the body. And there's a strain relief, and it is a very thick strain relief that connects the tube to the handle. On the back end, that's number 5, there's a strain relief that acts just similar to our other probes that connects the transducer back to its cable. And from there, everything is very similar. We have a strain relief on the handle, a cable, and a connector housing. So what do you look for when you're trying to inspect these transducers for damage? Well, it's important to understand what image quality looks like on the machine. So we're going to look at some examples first. We have transducer faults. Okay? We have a good air scan on the left here. And as we work our way across, we're going to see CW and phantom images. The important thing is to notice the uniformity. This is just shooting the transducer up into the air or on a body. The array is complete without any shadows, dropouts. There's no color or lightning, as well as the system is not throwing any actual error codes. When you have CW running, you have a good, accurate representation of pulse. There's no spikes, background noise, and you're not struggling to get that. You're not having to run the machine at 100% in order to see that pulse. Good phantom images, well, they just look right. The target is displayed as a proper size. It's not blurred, multiplied. It's not having any sort of array damage exposed by seeing maybe multiples of the same image. But also, you're seeing a nice smooth image all the way down from top to bottom. This does have to do a bit with how you set up your machine, but importantly, you shouldn't have any variances when you're just running it on a basic settings. So let's talk about a fault. What's color noise? Well, color noise appears when in the image when there should be a lightning flash or constant image quality. When you're looking at the video that's playing on the left right now, you can see those spikes that are running all the way to the top of the image. Those are actually what we call drops or spikes in image quality. On the bottom, you can see the dark color areas. That's where we're starting to have a dropout. So what is this caused by? Well, this is caused by damage to the lines. Maybe the shielding is coming off the 42 gauge copper coax lines, or they're rubbing together, or they're not touching at all. Constant color noise is often array damage, so maybe it's been dropped on its face, or it has not been handled properly. What do we do? Well, the probe needs to be disassembled, every line needs to be tested, and anything that's broken either needs to be replaced or soldered back in place. Remember, we're talking about a coax line that's 42 gauge, but the size of a human hair. So soldering those back in place can actually be quite the task. So CW noise, or continuous wave noise. What does this look like? Well, on the left we have some dropouts mixed with some spikes. You can see the bands going all the way side to side. And in the video, you'll see in just a moment, suddenly it's going to shoot to 100% and have tons of noise because we're bending that strain relief, and making noise come out of the transducer. There it is. So that's just jiggling the cable. That's just moving the housing around. CW is extremely sensitive, can pick up on the smallest of sounds, and continuous wave noise is a static or popping on the screen, interfering with clear reading, and it can be constant or intermittent. Again, this is usually circuitry or components that are failing in the connector, but it can also be the lines damaged in the cable. And of course, the repair actions are find the damage and diagnose and repair it. Dropouts and shadows. So when the part of the image is missing where there should be white probe imaging, or basically you should see the array, that white line at the top is actually the array seeing itself or the rubber compound in front of it. When there's a dropout, that occurs when the probe is engaged, and most likely there's either damaged lines or a section of the array itself is damaged. At this point, the transducer needs to be disassembled and test for those failing components. Artifacting. This is what it looks like on your machine, and it's always a fun one to diagnose because now we're starting to get errors that can also be part of the machine, not just the transducer. So you got to start diagnosing both ways. This can be a sunburst, a halo, a ripple, and it's usually the probe seeing something that's not actually there. This can be due to things like operational issues, broken lines, a damaged array, but it can also be failing cards in the system or boards, or crosstalk that is caused by fluid being inside the housing. What we do at Summons, we actually dehydrate the transducer as soon as it comes in the door. It usually takes about 12 hours. And then we inspect it for corrosion and any sort of damage from liquid before we start diagnosing it any further. The main reason for this is when you start seeing things like artifacting and you have liquid inside the transducer, it's only a matter of time before you have something possibly arc and damage the transducer even further. High voltage errors. Now we're getting into that really gray area of it being the machine. A 005 and my favorite 007 error code is actually caused by loss of ground or high voltage on the transducer. We're using Philips as examples here, but these can happen on GE, Siemens, and Accuson, Toshiba systems as well. They don't show the same code every time. This can be cross-talking, shorting out. This is usually caused by fluid intrusion or physical damage to the transducer. On the system side, it could be a loss of ground or a faulty power supply. Transducer faults, other error codes can include things like EEPROM chips not storing the transducer identifier properly. The chip could be damaged, the connector could be damaged, the housing may not be locking properly to the system, or there could be fluid intrusion. There are other error codes that can show transducer problems. This is always a fun one. Transducer mirroring. Using a phantom, you can set out some targets, and you'll actually see targets mirroring themselves as they go down through the array. Or on a wide view, we can see right at the 50 mark of the transducer, the phantom seems to repeat itself going to the left. Usually a connection problem because the probe is using its own information to fill in the missing information. Fluid intrusion, physical damage can cause these problems, and it can actually basically ruin your transducer at that point. And then no array. No array is when you don't have that nice solid white band at the top of the image. This again can be due to the actual array separating from its lensing material or fluid intrusion getting in between it. Articulation issues. Well, when it comes to a T-probe, it's actually kind of basic. It's a cable steering mechanism. If it's not flexing properly, it may be due to the drivers that move around, causing a strain on the cable, and it needs to be recalibrated, or the cable itself could have broken. This can be due to corrosion or just stretching over time on wear and tear. Problems with angle rotation. So the array is not able to rotate inside the head of this transducer. The probe here is not an X72T, which uses a matrix array to view, but this is an S72T. This is one that uses a driveline or motor controller. This could be corroded from fluid intrusion. It can also just fail over time thanks to switches or just bad electronics from manufacturing. Is that really a bad thing? No, electronics aren't meant to last 100 years. They do fail. Bite marks. This happens on TE probes. And this is where visual inspection really starts to play in. We've already talked about moving strain release around, checking housings, but this is where T probes, a high-value transducer, should be inspected at least on a monthly basis for scratches located on the head, lens, bending rubber, rings, and insertion tube, as well as discoloration. If you notice in the lower left, it's actually brown, cracked. You can see the rubber starting to fail, just like an old car tire. I don't think I want to use that during a study anymore, but a bending rubber is a quick and easy replacement, as well as cleaning up the head and buffing out all those scratches for patient comfort. This can also lead to a more expensive failure, like we were talking before, fluid intrusion, or even damage to the steering cables. Now, what I usually tell people at this point is grab a magnifying lens, and someone in infection control, OR, or biomed should be checking out these transducers as often as possible. Bite marks. Well, these are always a little tricky to identify, and it's a hole in the bending section of the probe. Everyone in OR always says they use bite guards, but it is possible to crunch on it with a molar or a canine, even if that bite guard's not sitting properly. The downside for us is these holes are about the size of a needle hole, so they're very hard to identify. If you're familiar with electronics and know these little yellow tags that you see in the image, that's about the size of a pencil head. And then the hole next to it's even smaller. But that is enough to let some Sidex OPA leak in and cause damage to the electronics inside, or even worse, create contact for a possible electronic shock to the patient. This is where leakage testing comes in. Leakage testing would actually expose this fault to you unless you know to send the transducer in for repair. Depth markers. We can see here they're worn off. The 39 is missing entirely almost, and the 20 marker is falling away. This can be from bites or scratches during the procedure, but also just wear and tear, or too strong of a solution during cleaning. Let's take some examples of fluid intrusion. Well, we have a can here that was actually dumped into a sink full of a nice amount of liquid, and then we have Sidex actually dried on the steering mechanism of an X72T. This previous fluid intrusion can be very detrimental because it can start to crystallize and build up. Even worse, when the fluid's still in the transducer, we have it causing damage to the components in the steering mechanism in the top left, and this is actually one of those bending rubbers with the tiny hole being pulled off of a T-probe, and you can see the liquid on the table. That is Sidex OPA. That's actually eating away at the components inside, and you can see it's already deteriorated the mesh on the transducer. And then burnt pins. Well, these are simple electronic failures. You can actually see the pins have been burnt. It's usually liquid damage or proper locking to the transducer to the machine. The transducer is being engaged, maybe with fluid active, and a spark or short has burnt the pin. This needs to be cleaned, and the transducer needs to be inspected. The next example I have for you is a lens seal failure. So earlier you might have noticed that nice white ring around the array. Well, obviously it's not nice now, but we actually have that seal compromised on the head of the transducer, and this is allowing stomach acid, Sidex, to go behind the array and start damaging the components. This can be caused by bites, harsh sterilization procedures, even just time on the transducer, because most of these transducers go through 2 or 3 ops a day they're being cleaned really quite often and fast. Oil defects. Well, these are kind of basic, just like your car. The transducer may have had a crack or damage from a drop and started leaking oil from the transducer. Now this oil acts as a protectant from friction, but also bridge for probe imaging. So bubbles in the oil can cause shadows and dropouts, and are a very good indicator that something like your V62 in the image here was not imaging at all because it was leaking so much. This can be avoided by inspecting the probe regularly and making sure that that oil is still in the transducer. If your department complains of oily residue, you know you need to have that inspected right away. Lens defects. I think this lens is fairly defective. On the left, you can see here it has peeled away from the array and even exposed the array to the open air. Now this is a probe that has been mishandled and was hit with a strong solution of cleaning. Depending on the type of damage, it can usually be improper storage or cuts from tools, even needles, and the lens will start to bubble and peel away. Sometimes it can be polished or refilled, but most of the time the lens has to be remade and relayered onto the transducer. A basic error, but often plagues transducers, is just cuts in the cord. Sometimes the cord will take cuts or be rolled over by machines, but you do want to inspect the cord for these types of damages. As we said earlier, you can start having dropouts and misconnections on your transducer because of these. And here's some damage from those solid strain reliefs we were talking about. The strain relief protects the cord from being strained, but once the strain relief itself fails, the cord starts to separate. And once you have the separation, electronics are exposed, but also the cables inside are starting to be stretched, and they're electronic cables, they're coax, they're not meant to carry the weight. And then we have discoloration. Discoloration is caused by typically the cleaning wipes the department uses being too heavily soaked in iodine. Chemicals used to sterilize the probe can cause this discoloration, and the downside to this is also showing you that you may be causing damage to the cable due to too strong of a chemical mixture. Then, of course, some simple electronic things like bent or broken pins. You want to inspect for these and make sure that your system isn't connecting the transducer with a bent or broken pin, and may actually cause some further damage to the transducer because of an electronic fault. My next favorite one, and remember these cans are made of cast iron, bent cans. That would take a lot of work. Good damage there. This is a metal can that is used to ground the transducer to the machine, and sometimes you will have compromised metal, cracking, maybe screws are missing. You want to make sure that that's always intact because that is the final connection of the transducer into the system for that transmission to ground. And then this always plagues everybody, a broken or loose locking knob. The locking knob on the probe is an engagement that locks it into the scan head. It is plastic. It turns a metal pin, but if it's not lined up properly, the plastic is designed to crack here so that you're not causing any bent or broken pins, hopefully. The locking knob is easily replaceable, but it is something you should inspect for often. Typically just turning the knob and then looking into the crevice will tell you if it's cracked or not. All right, guys. So I wouldn't be doing my job if I didn't talk about Summit a little more. We can offer the lower total cost of ownership for healthcare facilities, and we do this a few ways. We provide complimentary, same-day comprehensive evaluations. We call them discovery reports. They include images like what you're seeing on the right side, a full detail of what's happening in your transducer. We do not charge for those repair attempts that we may fail at, or as well as those evaluations. Our average repair turnaround time is 2 days. Most of our competitors are staying at a lot longer of a turnaround time, causing you to keep the loaner in-house longer and potentially causing damage to that loaner, doubling your cost. We only use OEM parts and materials and rebuild the transducer to their specifications. We have safe and reliable transducer repairs that last well beyond our warranty, and we are able to repair probes that even our competition deems unrepairable. Should you have any questions, feel free to reach out to me anytime or give us a call at 866-586-3744. I hope you enjoyed our presentation today, and I'd love to hear any questions you have.
Okay, thank you, Kyle. We do have a few questions for you. The first one is, do you have any suggestions on how to PM or inspect your transducers now?
So the visual inspection is the most important thing for PMing these transducers, and it's not a very involved process. It is simply inspecting it with the naked eye. Even better if you can get a magnifying lens. Even one from a dollar store would do the job for you. But doing this on a regular basis and catching transducer faults while they're early will cause, say, a lower cost repair than something 6 months down the road that's actually then turning into a high electronics failure and almost guaranteeing a transducer exchange at that point.
Okay, thank you. Do you think the FDA is going to help create policies that improve the care of these devices?
I definitely believe so. Right now, the required PM schedules are not very frequent, but also third parties are not held to any sort of standard in repairing these transducers. Summit Imaging has the ISO 9001 and 1345 for transducer repair and parts repair, and we are one of the only manufacturers in the United States that have that for both sides of the ultrasound business.
Okay. Do you have experience with a phantom in your shop, and can you accurately diagnose a probe using it?
So we use phantoms on our line every day on both testing the systems as well as the probes. Every technician on our line uses a phantom to check image quality and send before we strip the transducer. We provide the images from this phantom to our customer so they can compare as well.
Okay. Have you noticed the difference in image style and quality between the different carts before?
Yes, I have noticed lately that the GE systems tend to have a lot cleaner of an image with less lines of resolution, while Philips tends to dump more information into the image, but can sometimes be grainy and oversaturated. This is really just a taste and style choice that a lot of sonographers and imaging directors have in terms of what systems they choose. But every year, they slowly close the gap with resolution and image quality between the large manufacturers like GE, Siemens, and Philips.
Okay. Does Summit offer free loaners?
Summit Imaging does offer free loaners. We carry a very extensive inventory, and we will ship a loaner overnight to our customers, and they can use that box to then ship their transducer in for repair.
Okay. How is a leakage performed on a T probe?
Leakage testing is performed depending on what style of tester you have. There are some from BC Medical Group, Fluke, Biard. They are typically placed into a tray or tube that has a node in it. You then provide current to the transducer using a tester, and if the node in the bath of saline solution that the transducer has been placed in detects electronic leakage, it'll give you a failure or a pass.
Is leakage testing trending towards mandatory?
Leakage testing is trending towards mandatory. In fact, the American College of Echocardiology has made it a requirement in order to maintain their certification. And their certification is typically used for insurance payout, so a lot of hospitals follow it. That became effective as of January 1st this year. A lot of hospitals are having a hard time starting to do it, though, because they did not define the process and the requirements of tracking along with it.
Okay, thank you. What about non-T probe leakage testing during a PM?
It is, especially in endocavity probes, necessary, but there's no policies written around it as of yet. One of my favorite systems that can actually clean these probes for you and will soon become part of a leakage system as well as Trophon is working on something of that nature.
Is there any way to field repair small cuts on a probe lens?
Field repair small cuts? Not that I'm aware of, because of most field available chemicals or solutions or epoxies will actually cause more damage to the lens or affect the image quality. Mind you, most of that damage that you can see is not affecting the image. So you want to see if the cut is deep, if it's all the way through, if it's a scuff, and potentially if it can be buffed out. One of those things that we do when we inspect those transducers, when they come in for those free evaluations, is see if there's something that is quickly and easily repairable, and we keep that cost low and pass it on to our customers.
Are PDI purple top wipes safe to use on probes?
Purple top wipes? I do not remember the chemical mixture for purple top wipes, but those, you should follow the recommended cleaning products out of the OEM manuals for your transducer.
Can you touch on electrical safety for the transducers?
Can I touch on electrical safety for transducers? I mean, the potential of leakage and issues to the patient? Well, TE is, I'm sorry, rhetorical question to myself. TE probes that are used in studies inside the body are very susceptible to these problems, but also at a higher risk of electrical failure. The downside is they're also used in an endocavity study, so they're closer to internal organs and cause more damage. One of the things that really gets to me, though, is when you have electrical safety or electrical leakage on a transducer that's failing, that means there's usually a physical hole or gap in the seal. So now you might have something like Sidex or stomach acid inside the transducer as well that could then come out into the patient. And this is where a lot of issues have happened in OR before. Electrical safety is something very important to upkeep on these transducers, though.
Okay, thank you, Carl, and thank you again to today's sponsors, Summit Imaging. One lucky attendee will win lunch for their whole department. Details are included in the post-webinar survey, which will appear on your screen shortly. You must complete the survey to obtain your certificate of attendance. If you do not see the survey, email us at webinar@mdpublishing.com.